Hello everyone, this is a video lecture for the course ENSC107 Fluid Mechanics. It's a 3-unit course, and in a regular semester it has 5 hours per week of lecture and laboratory. But since this is offered in the mid-year or summer, then we'll have around 3 to 4 hours per day and 4 days per week. Okay, so I have already uploaded the syllabus and other course materials in our classroom, but I'd like to point out here our grading systems. Now we have final exams and homeworks, so a total of homework of 60%, and the final exam is 40%. That's around 100%. Okay, and the grading systems for or the grading scale is also in our syllabus. Okay, so you can just check about it. And then another thing that I'd like to highlight is the course policies. Please read our policies regarding attendance and homeworks, especially this one. For an online setup, for the homework or a calculation exercise, I have also uploaded the guidelines for solutions of your homeworks. Okay, this is it. Now please read and understand the contents of these guidelines, because this will be the basis for checking your homework. Okay, so it says here for number 1, all solutions shall be written in a solution sheet template unless otherwise allowed by the instructor to use other paper. What I meant by solution sheet template is this one. So I have given you a copy for this, and you can print this one. Okay, so it's like a graphing paper or something, except that it's more tailored for us here and for my preference. Okay, so now let's go to number 2. It says fill up all information required in your solution sheet, example problem number and sheet number. Okay, so it says here, for example, the name, you write it here, and then the ID number, the section, and then the problem number. Now, what problem are you solving in this sheet? And if in case it will take you like 3 sheets per one item, then you should write here 1 of 3, or 2 or 3, or 3 of 3. Okay, now in case you don't have means to obtain this or to print this solution sheet, then you are also allowed to use alternative option. But it must be of the same size. That's 8.5 by 11 inches letter size paper, and must be drawn with borders having the same as that to our solution sheet. Okay, so for an example of this is this one. Okay, so this is one output of one student here. So you see that we have that he draw the borders and the templates exactly the same, right? So again, you can use just a bond paper size, a bond paper, but you should be able to draw the same borders, the same contents of the templates. Okay, what else? Now let's go to number 4. It says here that the solution must be written in a clean, clear, and complete manner. Now these 3 right here, they're the ones that governs the checking of your homeworks. Okay, so it must be clean, it must be clear, and it must be complete. And when I say clean, refers to that the homework output has no erasures, and it also refers to scanning issues, so it must be scanned properly, and other formatting issues. Okay, so just like this example output, you would notice that they tried to really write it neatly and straightly. Okay, so if you have a handwriting that it's like inclined, so probably that would get deductions. Okay, so also erasures, should have no erasures for in your homeworks. I usually give 5 points deduction for every erasures, so even if it's just typos, I give 5 points deductions to that. Okay, next is the clear. So clear refers to the clarity of the flow of the solutions and calculation process, that you understood the calculation process even though you did not arrive to correct answers due to typos or minor issues. Okay, so what I meant by that is another example output here. So first, there must be something like a translation of the given words into illustrations, and then you must write the given, the required, the given data, and then the required data. What are we solving for? And then your solution would start, for example, this one. So solution, so solve for mass flow rate. Okay, so every line or every process here, solution process, there must be some line labels. It says here, for example, solve for mass flow rate. And then after you solve for the mass flow rate, you said solve for a known gas velocity, for example, in this case. And you have to also provide captions. For example, this is equation 1, so you have to write equation 1. And for figures, for example, figure 1, so there must be some captions. Okay, so that's it. That's the clean and clear. Now for the complete, it refers to that all problems were answered even if the answer is incorrect due to typos and minor issues. Okay, so it's all there in our solution guidelines. Okay, another one, the next one is number 5. Depending upon the problem situations, the solution can be written in a lengthwise manner or crosswise. Okay, so usually it's written in a lengthwise, right? So if this is the space, then you have this line right here. It's actually divided into 2 or divided into 4. You can use that. I mean, that line is intended for that division, so that you don't need to measure anymore. So you just have to project the line, okay, from top to bottom. Okay, so that's just an imaginary line. Okay, so you notice that it goes from top to bottom, and then you go right here, then bottom. But it is also possible to write it in a crosswise manner. Okay, just what I've included here in figure 4. Right, so this one is lengthwise, this one is crosswise. Okay, so just in case it's not enough, I mean the space is not enough for the half, for just a half. Okay, and what else? There should be only one problem per sheet. No multiple problems in one sheet allowed, unless otherwise permission is granted to do so. So meaning that use only one problem per sheet. Okay, so in this one sheet, that's only one problem. Again, unless otherwise permission is granted to do so. The number 7 is to box all final answers. All final answers must have its unit written beside. Okay, so for example, we have here, let's say the pressure drop is 2777 pascals. Okay, so it must have a unit. Okay, and then number 8, all steps of the process must have labels or descriptions about what you are solving at that particular process. Just like this, it says here, so substitute the computed data to equation 1. Okay, so that is why it is necessary to put the caption on your equations and your figures, because sometimes you might have referring to figure, for example, figure 1 or figure 2, then the diameter of the pipe or something like that. Okay, so there are still other rules here for scanning issues, right? You can just read the contents here about scanning, but the main point here is if you scan it, it must be properly scanned, and when I say properly scanned, it must be something like this. Okay, so you have to make adjustments in terms of the brightness. So an example right here in figure 6a, this is a good example, very good example of scanning. Okay, and this one on the right, that's a very poor example. Okay, so that would get a large deduction, probably maximum deduction for this type of outputs. Okay, so when compiling the file, also make sure that you have this proper file name. For example, our course code right here in ENSC107, and then dash, it's homework 3, and then dash your last name, then underline first names or first name initials. Right, so if that's homework, then we'll use homework HW, and if it's a long quiz, then LQ. And for term exams, that's DE. That's going to be our file names. Okay, so I guess we'll now get into the contents of the course. It's in our syllabus, and you can just briefly browse it here. So first, we'll talk about the introduction to fluid mechanics, the properties or the difference between a fluid and a solid. And then after that, we'll discuss a topic on pressures, pressure and hydrostatic equations, as well as the pressure measurements. Okay, and then after that, we'll move on to forces on submerged surface. What if a surface, a solid for example, is immersed in a fluid? Then because of that pressure, we can actually translate that pressure into a force. Okay, and then we'll also discuss the buoyancy and stability. So why does a body or an object floats? Okay, so that's in this topic. Then after that, we'll move on to the fluid flow and Bernoulli's equation. Hey, what would happen if there's a moving fluid, let's say in a pipeline or in an open channel, for example? Okay, and then we'll use this Bernoulli's equation to solve some stuffs. And then we'll use after that, we'll move on to the general energy equation. Then the applications would be the pipe flows, open channel flows, and then external flows. Then lastly, we'll talk about fans, blowers, and compressors and pumps. Okay, so for this one, we can say that this is more on statics, fluid statics, meaning it's not in motion. But starting here, it's going to be dynamics, and this one is the starting from pipe flows. That would be applications. That's applications. If we write it here, we have applications in terms of the pipe flow, open channel flow, then what else? We have external flows. What it means by this is that, for example, we have a pipe, a circular pipe, and there's a fluid inside here. Okay, and that's going to be pipe flow. Or you can say internal flows. Now this one, for open channel flows, you can have, let's say, a canal, for example, and we have a fluid right here. And this fluid is exposed to atmospheric pressure. Okay, so the governing equations would be different from that of the pipe flow. Then for the external flow, say an airfoil. Right, so there's a moving fluids right here, and then this is a solid object. Okay, so what's going to be the principles beyond that? Principles in that situation or phenomenon. So that's going to be about these external flows. Okay, and lastly, we'll have a topic on selection of fans, blowers, and pumps and compressors. Right, so I guess that's enough for this course introduction, and we'll start our discussion in the next video. See you in the next video.